so let's see the equation presented on the previous slide with Planck's constant in action. So beta carotene is inside of carrots. It's what gives the carrot that signature orange color. This particular compound absorbs light at 450 nanometers and 470 nanometers. Now, both of these wavelengths of light, if we observe the electromagnetic spectrum, are kind of blue/purple in appearance, which, since this is the wavelength of light being absorbed, the opposite on the color wheel, or the complementary color, is going to be what we see, which quite visibly is orange. That's exactly the color of carrots. So everything so far making sense. Well, let's pick out one of these wavelengths. Let's focus on the 450 nanometer light. The question is, how much does one photon, one particle of light that has a wavelength of 450 nanometers have in joules? How much energy is there? In addition, we can ask the follow-up question, instead of just one photon, what if we had 1 mole of photons? How much energy is present there? All right, well, the equation that you're going to need is going to be the previous equation that we learned. E is equal to h nu, also equal to hc divided by lambda. And aside from watching the units, I'm just going to let you guys try and work through this problem. How much energy does 1 photon of 450 nanometer light have? How about 1 mole of those photons? All right, welcome back from the pause. Where we're going to start solving this problem together, at least what I'm going to demonstrate. First, we're going to pay attention to the units. Pay attention to units. Right, we have nanometers here, there's joules, there's moles. We want to make sure that all of the units that are currently presented to us are all going to actually be playing together in the equation that we're going to be working with. All right. 2, we're going to plug and chug. Pretty common phrase. We should have all of the pieces of information that we have. We're going to plug them into the equation. Again, paying attention to the units, making sure everything that we don't want cancels out, and everything that we do want will remain. All right, so first, we're paying attention to the units. In the equation that we are working with, first we need to pick out which portion we need. Do we have a frequency or do we have a wavelength? Well, looking at the wording of the problem, we're specifically told that we have a lambda equals. There is a wavelength here. Units are present in distance, which means, again, we are paying attention to wavelengths. So that means that we're going to need the E is equal to hc divided by lambda version of this equation. E is equal to hc divided by lambda. All right, so speed of light, we know, again, Part 1, we're going to pay attention to the units. Speed of light, we are told in meters per second. We can use the same speed of light that we saw in Part 1 of this lecture. Planck's constant, we just saw, is in unit of joule seconds. So we can see already that the 2 seconds are going to play together. They're going to cancel out, so we don't have to do anything with these constants. The wavelength that we are told is in nanometers. Here now we can see that there's a little bit of a discrepancy, right? Speed of light is in meters and the wavelength is in nanometers. So even before we take the values that we are given, these 2 different constants, h and c, we're gonna have to convert our wavelength into meters. That way it will actually properly cancel out when working with our speed of light. All right, so the wavelength that we are working with specifically is the 450 nanometer wavelength. And this 450 nanometer wavelength light, we're going to have to convert into meters. Well, the metric prefix of the nano means that there are 1 billion, or 10 to the 9, nanometers in that 1 meter, right? Nano just means 1 billion. The way that I personally remember which prefix nano means, like what nano means, is that nano starts with an N. And the number 9, which is in the exponent here, also starts with an N. Right, so nano means that you have 10 to the 9 of whatever unit it is that you're working with. In this case, it just happens to be meters. So hopefully that's a little mnemonic that is useful for other people as well. All right, so if we take 450 divided by 10 to the 9, our nanometers here canceling out, we are going to be left with a distance that is equal to 4.5 times 10 to the negative 7 meters. I should say 4.50 if we're keeping with proper sig figs. Again, earlier I said I'm not a super huge stickler for sig figs, and it's already starting to show. All right, so 4.50 times 10 to the negative 7 meters. Now we can see our unit of meter is present, so this is going to be what we can insert into our equation. Now we have a wavelength in meters. I am going to clean the slide just so I have more room to write. So if you're still writing this stuff down, pause the video quick. I'm going to erase. All right, rewriting the equation that we need, E is equal to hc divided by lambda. And now we can actually start plugging and chugging. We can take our constant h, which is 6.626 times 10 to the negative 34 joule seconds. Our speed of light is 2.998 times 10 to the 8 meters per second. And our wavelength, which we just calculated, is 4.50 times 10 to the negative 7 meters. So the seconds in the numerator are going to cancel out since we're taking a second in the numerator and multiplying it by an inverse second, going to cancel out. We have a meter in the numerator and a meter also in the denominator. Those are going to cancel out. And so the only unit that remains we can see will be the joule. So this is great. This is going to give us a calculation straightforwardly for what the energy of a single photon of this one particular wavelength is going to be. So the unit of energy that one single photon of 450 nanometer light has is 4.41 times 10 to the negative 19 joules. So we can already, just off the bat, see that this is a very, very tiny unit of energy. And the number is so small that you might, again, be kind of tripped up at first. If you're critically evaluating your answer, you're like, oh, this seems too small, like this can't be right. Remember, this is the energy of one single photon. One teeny tiny little photon. We're on the quantum scale, where masses are very small, energies are also going to be very small. So this actually, in its very small magnitude, makes perfect sense. Something on the value of, or on the magnitude of 10 to the negative 19 is perfectly acceptable for the amount of energy that a single tiny particle is going to have. All right, but what if we had something that was more macroscopic? What if we had 1 mole of photons? So not one single photon, but instead a mole of photons. Well, in order to scale up this value, what we need to recognize is that, just like before, when we first introduced the mole, 1 mole is equal to 6.022 times 10 to the 23rd of whatever. In this case, we're going to be looking at photons. Before, we looked at atoms and molecules, but again, a mole is just 6.022 times 10 to the 23 of whatever. So if 1 photon has 4.41 times 10 to the negative 19 joules of energy, 6.022 times 10 to the 23rd photons is going to have that much more energy. We're going to scale the whole thing up. How this looks with dimensional analysis is going to hopefully make my description a little bit more clear. So we're going to start with our 4.41 times 10 to the negative 19 joules. And again, this is per photon. We're going to multiply this by Avogadro's number, where there are 6.022 times 10 to the 23. In this case, we are working with photons. And this is all per every 1 mole. So if 1 photon had 4.41 times 10 to the negative 19 joules of energy, and now we're scaling it up by Avogadro's number worth of photons, all we have to do is similarly scale up the energy. So we're going to take the unit of energy we just found, multiply it by Avogadro's number, and this is going to give us a value of energy that is 2.6 times 10 to the 5 joules per every mole. Now, this is a unit of energy that is much more appreciable on the macroscopic scale. This is a unit of energy that we would be able to like feel as thermal energy, or we would be able to see as visible light.